Okay, looks like I am live. Okay, awesome. Vanakkam. Okay, just let other students also know that Shreyas Sir is live back onto a new video link. So make sure that you share this link with your friends just in case, but I will be asking my team also to share this link on Telegram channel as well as put it up in the comments of the previous video. Okay, so let's continue guys where we left. Okay, so yep, good afternoon everyone. Yeah, smash the like button quickly. Smash the like button, mark your attendance quickly. Everyone start marking your attendance quickly. Get all the kids out here on the new stream. Okay, we are continuing with whatever we left with. Awesome. Okay, now like I was saying just before the stream got ended was that in Ampere's loop law, remember that you always have some wires which carry current. Let's say I1, I2, I3, I4, so on and so forth. You start from a point and come back at the same point. At every point, you measure the field and find the distance, multiply them, field into distance. You add all them up, that means integration. Because you're coming back to the same point, that's why the cyclic integral. The value of magnetic field with the length that you are traveling, the addition over the complete loop is permeability into current which is inside. Now when you go in this loop, the currents which are inside are I1 and I2. I3 is outside, so do not count it. Just like in Gauss's law, you take inside charges, so you only take the charges here, the currents which are inside the loop. But the currents also have sign. Keep this in mind. If the loop is going this way, then take your right hand like this, the thumb goes up. So all the currents in the direction of the thumb are positive. All the currents in the opposite direction of the thumb are negative. All the currents in the opposite direction of the thumb are basically going to be negative. Is that clear, my dear students? Everyone understood this point? Clear? Perfecto. Moving ahead. Okay. Using this Ampere's law, you find the magnetic field of few more geometries like solenoid and toroid. This is a solenoid. Solenoid is nothing but many coils placed one after the other. One turn, next turn ahead, next turn ahead. So like winding a tube, not a ring. It's not a ring, it's a tube. So there are many coils on the tube. You will see there will be magnetic field inside that tube of coils. That field is mu naught n into the current. This n, be careful, it is number of the turns per unit length. It's small n. So it is basically total turns upon total length. Usually capital N is used for total number of turns. Keep this in mind. But if you take a solenoid, which is nothing but a tube, you bend it and you connect the open ends, what you see is nothing but a toroid. So a toroid is nothing but a solenoid which is bent so that there is no open ends on both sides. So it's like into itself. It's like a snake eating its own tail. Imagine a snake eating its own tail. Can you visualize that? Yep. This is a continuation class, Shruti. This is a continuation class. The previous class just got ended because of some tech issue. So then it is a toroid. Then the field inside is mu naught. Total turns, capital N is total turns into current by 2 pi r. If you are wondering what r is this radius, not this radius. Is the radius of the toroid, something which you should be aware of. Now, if you take a wire which carries current, it creates a magnetic field around it. The magnetic field created by a single wire carrying some current, wire carrying some current is given by mu naught into current by 2 pi into r. R is the distance at which you are trying to measure the field. R is the distance. So if the current is going like this, if you hold your right hand fingers in the direction of the current, the curled fingers will point in the direction of the field. So current, this will be field. Thumb is current, this will be field. So mu naught permeability, I is current, 2 pi r is the distance at which you are measuring the field. If you go far away, the field will also reduce. So obviously, if you have a wire, it produces field. Now what if you have two wires which are placed close by each other? Then what happens is the field of one guy applies force on the field on the other guy, applies force on the current which is being carried by the other guy. Now the formula which you should remember is this one, guys. The force on a current carrying wire, the force on a current carrying wire is given by current into length into magnetic field, I L into B. This is the formula. I is the current going through it, L is the length of the wire, B is the field on it. So imagine two wires, one wire creating the field, other wire carrying the current. That field will apply the force. That force is given by mu naught into current 1, current 2 by 2 pi d. D is the separation between the two wires. So this B will be because of one wire, the force will be on the other wire. Now it so happens if they are in the same direction, then the currents will attract. Same direction, currents will attract. If they are opposite, then they will repel. So this is very, very important. If they are parallel, then they attract. But if they are anti-parallel, then they will repel each other. Okay, it's exactly opposite in charges. In charges, similar charges repel, but here similar currents attract. In charges, opposite charges attract, but here opposite currents repel each other. It's exactly opposite. Okay, so magnetic field due to a wire, done. Force on a current carrying wire, ILB. Force on two parallel wires, mu naught I1 I2 divided by 2 pi d. Keep this in mind. Moving ahead. If you take a loop of wire, a coil of wire, that coil behaves like a magnet. A magnet has two polarities, north pole and south pole. So it is nothing but a magnetic wise dipole. Hence, I can say a wire which carries current is just like a magnet with two polarities, hence a magnetic dipole. So a coil carrying current has something called as the magnetic dipole moment, which is just like your electric dipole moment. So I'll just put it over here. The magnetic dipole moment, just like your electric dipole moment. Always it's from south pole to north pole. It is a vector quantity. That formula is NIA. N is obviously total number of turns because it is capital. I is current. A is nothing but the area of the coil. What is the area of the coil? Big area, many turns, large current, very strong equivalent magnet, very strong magnetic dipole moment. If you look at the units also, it's not that difficult. The unit of this will be N is turns, so don't worry. I is current, so it will be nothing but ampere. Area is meter square, so it should be amperes into meter square. It should be amperes into meter square. Everybody with me on this? Clear? I hope this is understood. Anytime PV Chitra. Yes. I hope this is clear. Okay. The derivations list, whatever is there in NCERT, just do everything, bacha. But if you want a list, I'll try to see if I can get a list of all the derivations and I'll try to post it on Telegram. Okay. Okay. I'll try to do it. Okay. Cool. So now, just like electric dipole experiences electric dipole placed in electric field experiences torque, it rotates, and the torque is given by dipole moment into field. Same if you take a magnet, you put it inside magnetic field, it will rotate. So that means there is a torque acting on it, and the torque is given by M cross B. Instead of P cross E, recollect, here it is M cross B. So that is the torque which acts on a magnet which is placed, or a coil which is placed in somebody else's field. This is external field. This is external field. This is your magnetic moment, the magnetic dipole moment, which I have mentioned over here. So all these are important formulas, exactly similar in electric dipole moment. Okay. Similarly, you will also have to remember this particular formula, which is the magnetic field on the axis of a coil. See, just some time back, I had given you a coil and I told you at the center, the magnetic field is mu naught I divided by basically 2R. That is basically at the central point. But what if I am not at the center, I am at a distance x? At this point, what is the magnetic field? The formula is this one. Mu naught I, which is the current, R is nothing but the radius. So I'll just mark it over here. R is nothing but your radius. X is nothing but the distance on the axis. It's going to be slightly different. It is x square plus r square whole raised to 3 by 2, the whole thing into 2. So that's the change. So here mu naught I by 2 is there. Mu naught I by 2 is there. On the top you have r square. Here at the bottom you have r square plus x square raised to 3 by 2. So that's something which you should keep in mind. Okay, everyone with me? So in fact, if you put the value of x as 0, you will get back this original formula. So you can see the magnetic field at the center is also it also can be derived by putting the value of x as 0. By putting the value of x as 0, because you're at the center. If x is not 0, you're on the axis, then you're going to use this formula. This is on the axis. This is on that particular axis. You're going to use this particular formula. Is that okay? Very good. Awesome. Awesome. Sir, is M pole strength or magnetic? So some books use different symbols, guys. So let me also tell you, in some books they use capital M is small m into length. So it depends which book you are following. Technically, you should actually use capital M, and this is small m into L. And capital M is for magnetic moment, small m is for pole strength. But since if you have already used small m for the magnetic moment, then you can also write small m is equal to pole strength. You can write m pole over here into the separation, which is like 2m. So that way there is clear-cut distinction that this is dipole moment. This is dipole moment, and small m is for the pole strength. That is also okay. Okay? But make sure you mention what each symbol is in the answer sheet, or else the examiner will get confused. Next important point regarding magnetism, and that is important points regarding Earth's magnetism and bar magnets in general. So remember, Earth is also going to behave like a magnet, right? And the you will see the Earth's magnetic north pole and south pole contain the magnetic poles of the assumed bar magnet. So if this is the Earth, if this is your north pole, if this is the south pole, if this is basically the axis of the Earth's rotation, this is the axis of the Earth's rotation, you will see that if somebody brings in a magnet, a compass, a needle, then the needle points like this. The needle basically points like this, with the north going on the top and the south going at the bottom towards the south pole. The reason why that happens is because north pole gets attracted by the south pole and south pole gets attracted by the north pole. But you will be like, sir, here there is south pole and here there is north pole. How are they getting attracted? The reason is, although I call this as a north pole, technically over there at that particular point, you have the magnetic south pole. Here you have the magnetic south pole. Similarly, over here, actually what you have is the magnetic north pole, magnet-wise. So the Earth's bar magnet technically is like this. North is here and south is over here. So if you have to draw diagrams, you're going to show diagrams this way. Okay, the Earth's magnetic north will be down, magnetic south will be on the top. That's why the north pole of your bar magnet or needle attracts towards the south pole. That's why you call that as the north pole, and that's why you call this as the south pole. It's not in reference to the Earth's magnet, it's in reference to the magnet that you use outside. Okay, something which you should keep in mind. Everyone? Everyone? Clear? Okay, okay. I also don't know, Bacha, why the stream got ended. Even I was surprised. I was teaching, and thankfully I checked the chats, and everybody was like lag, and then the stream got ended. So I'm also not sure what happened. But it's okay. I contacted the team, and they were thankfully able to create a duplicate stream, and I was able to start the session. Okay. Another important thing is that you cannot isolate the North Pole or the South Pole. Magnetic poles can't be separated. You always get magnetic poles one on one free. Like you buy one, get one free, right? Same offer is valid for magnetic poles. You cannot separate them out. And usually you make magnets out of iron and its alloys because they are ferromagnetic in nature. Basically, ferromagnets are permanent magnets. So if you want to make a permanent magnet, you are going to use iron, nickel, cobalt like things which are ferromagnetic in nature. Okay, keep this in mind. Now, some additional properties of field lines in magnetism are, because you can see there are some similarities in electric field and magnetic field, but there is some distinction also. See, a field gives you the direction in which the magnetic field lines are traveling from North Pole to South Pole. You will also see that these field lines will never intersect, because if they intersect, then there are two directions of the field. So they will never intersect. They will come close, they will go far. If they are coming close, the field is strong. If they are going far, then the field is very weak. So the strength of the field is given by how many field lines are there nearby each other. If they are close enough, it's strong. If they are far away like over here, then it is a weaker field. The direction of the, if you draw a tangent, then you get the direction of the field. So if you draw a tangent, you get the direction of the field. So you will see they will never intersect. A tangent drawn always represents the direction of the net field. The magnetic field lines of a magnet always form closed loops. This is very different in electricity. In electricity, they start from positive, end at negative. They can start, they can terminate. But in magnetism, they don't do like that. They are always in the form of closed loops. They are always in the form of closed loops. They never start or they never end. You can see that. You can see that. In a magnet, you will see that they will start like this and they'll go like this. They'll start like this and they'll go like this. There is no start or end, actually speaking. There is no start or end. They are in the form of closed loops. Keep this in mind. Okay, whereas in electricity, they start from a positive charge and end at a negative charge. And this I already told you guys, more the number of field lines, then you will see the field is going to be very strong. Also, they do not intersect each other. That's also something which I have already mentioned to you. Next important point. I think torque I have already told. Torque on a magnetic moment placed in any field is m cross b. Similarly, remember energy of a dipole placed in electric field. It was field into the dipole moment. Here also it is the same thing, but obviously minus sign is there. So it is field into the dipole moment, but there is a dot product. Okay, keep in mind, because this is energy. So magnetic potential energy is minus m dot b. This is a dot product. If you want, you can write it as minus mb cos theta. What is theta? Theta is the angle between the magnetic moment and the magnetic field, just like in electric field and electric dipole moment. So electrical potential energy was minus P and E and cos theta. Here it is minus dipole moment into magnetic field into cos of theta. That's it. It's the same thing. If you remember one, you automatically remember the other thing. Okay, everyone with me? So that's the next thing. If you have opened up NCERT, if you are following through NCERT, you can see that I'm going in the same sequential order. So it's in fact better if you have already marked certain things, or if you have NCERT open in front of you. So as I'm showing you these formulas, you mark, okay, this is important because sir has discussed. Because many of you might not have marked in your NCERT, or you might have missed marking few things. So whatever I'm teaching here, make sure you mark it. Okay, fine. Let's move on. Let's move on. Next, magnetic properties formula. What are the different formulas in magnetic properties? You will see there is a property called susceptibility. There is a property called relative permeability. There is a property called just permeability. Okay, so what are these things? See guys, very simple. Just like mu naught tells you permeability of vacuum, mu m is nothing but the permeability of that medium. So that will be relative permeability, relative, it's a number, into permeability of vacuum. So if I say for vacuum, it is some number into 5, into 3, into 0.9, into -7, into -3, whatever that number, that gives me the permeability of that medium. This number is nothing but your relative permeability. Relative permeability. It's just a number, it does not have units. Okay, so this is your relative permeability. Now this relative permeability is related to a number called as susceptibility. So relative permeability is nothing but 1 plus susceptibility. This x is nothing but, this x over here is nothing but called as the magnetic susceptibility. So it's just a number, it's just a quantity which has been defined. So susceptibility plus 1 is your relative permeability. All these are important formulas. Now, different materials have different relative permeabilities and different susceptibilities. Something which you should be aware of. Just to give you an idea, there are 3 kinds of materials. One is diamagnetic, other is paramagnetic, other is ferromagnetic. Now, if I talk about basically relative permeability, and this is relative, which is 1 plus your susceptibility, which is basically x. For a diamagnetic material, the relative permeability, guys, the relative permeability is less than 1. Yes, it is less than 1, it is less than vacuum. So in fact, you are going to put a number like this, less than 1 over here for diamagnetic materials. For paramagnetic materials, it will be like 1.2, 2, 1.7, 1.98, 2.225, something like that. So it is more than 1 for paramagnetic. For ferromagnetic, it is very large, like 200, 1000, like that. So it is much, much larger than 1. Now, because of that, what happens is the value of susceptibility that you get here is actually a negative number, because x will be mu relative minus 1. So if this is like 0.7, 0.3 and all that, so it is less than 1 by some negative number. So hence negative is the value of susceptibility for diamagnetic. For paramagnetic, it is a small positive number. For small positive numbers of susceptibility, you get it as paramagnetic. And ferromagnetic means it will be a large positive number. Keep this in mind. Okay, everyone with me? Great. So guys, I think the lecture will get extended a little bit beyond 2 because we had a break and all that. The stream got ended. So I think I'll have to extend it a little bit more. Another important thing is, if you want to find the relationship between your magnetic field and something called as magnetic field strength or magnetizing field, then you can use this formula, okay, which is mu naught into relative permeability into H. H is basically your magnetic intensity. So H is usually your magnetic intensity inside a material. Magnetic intensity inside a material. If I'm applying a field, if there is some material like iron or copper or wood, what is the magnetic intensity? You use this formula. B is your magnetic field, that is completely different. This is a new quantity called as magnetic intensity. So these formulas very rarely get asked, but just in case they ask you, then you are going to use these formulas. That's all. I mentioned all these things before also. So for diamagnetic, paramagnetic and ferromagnetic, whether it is more than 1, less than 1, etc. Now, moving ahead to the next set of formulas, we are coming up to Faraday's law, electromagnetic waves, EMI, all these things. Faraday's law, guys. Now, in Faraday's law, it's all about creation of electricity using magnetic field. So if you take a bar magnet and you expect current, that's not possible. But if you take the bar magnet and move it in, out, left, right, top, bottom, you will see the field lines will change through the coil, the flux changes through the coil, because of which electricity gets generated. So Faraday said that electricity can be created by magnets by moving them or turning the coil or creating relative motion, because of which the field lines passing through the coil change over time. That change in the flux, the change in the field lines, creates electricity inside the coil. So the relative motion, very important word, relative motion between the magnet and the coil is responsible for generation of the current in the coil. This phenomena by which you change the magnetic field and create electricity, that is called as electromagnetic induction. This is what you're going to mention in the board paper. What is EMI, electromagnetic induction? You change the magnetic fields, you change the flux, thus generating electricity. The EMF created is also called as induced EMF. Induced EMF. Induced EMF causes induced current. Obviously, induced EMF will be current into the resistance of that particular coil. Does that make sense? Induced EMF will be current passing through the coil into the resistance of that coil which is there, or that circuit which is there. Now, obviously, since we are talking about field lines cutting through a coil, that is area, so obviously it makes sense to define something called as the magnetic flux. Just like electric flux was electric field into area, magnetic flux will be, if you take a coil or an area, that will have an area vector, there will be field in certain direction, the area vector and the field will make certain angle theta. The flux of magnetism passing through it will be field into area into cos theta, or just the dot product of field into area. One and the same thing. This is your magnetic flux. So remember, this B symbol is used for magnetic flux, and this is your magnetic flux. And if I ask you what is the unit of it, it will be nothing but, this is Tesla. So 1 Tesla, this is nothing but area, so meter square. That has a new symbol called as Weber. So 1 Weber is the unit of flux. It is 1 Tesla of field passing through a meter square. That is 1 Weber of flux. Now, if I change the area angle wise, or if I expand it, if I change the value of B, then the flux will also change. So how can I change the flux? So phi B can be changed. Phi B can be changed by changing either the magnetic field, or by changing theta, or by changing area. If any one of these things change, the flux changes. If flux changes, then it generates EMF. This is our next statement, and that is your Faraday's law. So Faraday's law says that the EMF generated in a coil is how quickly you are able to change the flux. That means the rate of change of flux is the induced EMF. Is nothing but the induced EMF. Everybody with me? Everybody with me? Yes, sometimes the angle saying 30 or 60, I'm confused. Always measure the angle of the area vector, bacha. See, sometimes what happens is that they will give you a coil like this. They will tell you the field is this way, and they'll tell you this is 60 degrees. This is 60 degrees. The angle theta is not 60. Please be careful. No, it is not 60. Why? Because the area vector will be here. The actual angle that you should take is this angle. That will be 30 degrees. That is theta. So always measure the angle of the area vector with the field and not the plane of the coil. Okay, so that's a common confusion, not just in magnetic flux, but even in electric flux. Okay, super, very nice. Now, if you just look at it from the Faraday's point of view, if you just look at it from Faraday's perspective, you will see that according to him, the magnitude is how quickly the flux changes. That will give you the induced EMF. But you will see an additional negative sign. You will see an additional negative sign over here. Why is that negative sign? That negative sign that you see over here is because of something called as Lenz's law. What is Lenz's law? It is based on conservation of energy. It says that it's based on conservation of energy. It says that the direction of the EMF is always opposite to the change of flux, is always opposite to the change of flux. So if flux is trying to increase, EMF will be on the other side. If flux is trying to decrease, the EMF will be in the other side again. So it's always opposite. That's why you put the minus sign over here. Is that okay, bacha? So why that minus sign has come? Because of Lenz's law, which is based on the principle of conservation of energy. It says if flux tries to increase, the induced EMF will try to decrease the flux. If flux tries to decrease, then the EMF induced will try to increase the flux. So always opposing. Just like you oppose to whatever your teachers will say, or maybe your parents say. Your mom and dad is saying study, you're like, no, I want to play. If your mom and dad says play, you're like, no, I want to sit and study. So that is basically your Lenz's law. Exactly. Now, I think I have mentioned it over here also. Yes. So the polarity of the induced EMF always is such that the direction of the EMF or the current which is created opposes any kind of change. Like for example, if I'm taking this magnet over here, this north pole is coming close, no? You will be like, no, don't come close to me. So you will repel it. So how do you repel this magnet? By creating a north pole here and south pole here. So this north will repel this north, and that's how this will be opposed. So if you want to create a north here, south here, hold your thumb from south to north. Your fingers on the right hand will curl this way. So that's the direction of the current. If you take the same magnet away, then in this case, it will try to be attracted by it. It will try to attract that magnet because it's going away, always opposing. If it comes close, stop, repel. If it goes away, bring it back, attract. So this north pole will be attracted by south pole here. So this is how the magnet will be formed because of the current created inside the coil. So if the magnetic moment is that way, hold your thumb that way, your fingers will curl this way. So that's the direction of the current. So that's how simple it is to use Lenz's law. Just see what is happening, try to oppose it. Whatever is happening, try to oppose it. Is that okay, guys? Is that okay? Very good. Awesome. Now, if you take a wire or a conductor or a rod and move it inside a magnetic field, there is an EMF created. Because you are moving a rod, that's why with the word motional. Because you are moving in a magnetic field, you will see that there will be polarities created across the rod. So that means that it will behave like a battery. Hence, motional EMF. Motional electromotive force or motional EMF. That's the word used. And that comes out to be as B. So like I was saying before, a moving rod in a field behaves like a battery whose voltage is BLV, and that's how it produces the current inside that particular circuit. So you can see this rod is now just like a battery. You can replace it like that. So you can solve problems based on this then. Next important point is inductance. Now there are two kinds of inductances. One is self and one is mutual. See, imagine self-inductance and mutual inductance, the difference is as follows. Imagine your mom and dad say that go play outside. You are like, no, I will not play outside. I will sit and study. Your mom and dad say sit and study, you go and play outside. So you're always opposing what others are saying. If that guy says A, you say B. If that guy says B, you say A. So that is mutual inductance. So imagine there is a coil here and there is another coil. In this coil, there is some current which is changing. Because of that, it affects the other coil. If there is a change in the other coil's current, then it affects the current in the first coil. So it's a mutual effect. That is called as mutual inductance. What is it called? It's called as mutual inductance. In self-inductance, what happens? Imagine I'm studying and suddenly I feel like, no, I'm studying too much. I will play now. Now I go to play. I'm like, why am I playing? I should come and study. I only oppose my own thoughts. That is self-inductance. So there will be only one coil, and in that coil, if the current tries to increase, the coil will oppose it. In that same coil, if the current tries to decrease, again it will be opposed. So the changes are opposed in the coil itself. That is self-inductance. Whereas it happens in each other coil, that is called as mutual inductance. Now the formula for mutual inductance is as follows. If there is flux in a secondary coil, the flux of magnetic field flowing in the secondary coil, and I see that is proportional to the current in the primary coil or the first coil, then that constant of proportionality, the constant of proportionality is called as the mutual inductance, or just the coefficient of mutual inductance. So the current in the first coil causes flux in the other coil. So if you find the ratio, that is going to give you the mutual inductance between the coils. Okay, that's very, very important. Now, if you take two solenoids, one solenoid inside the other solenoid, that is obviously a mutual inductance. Now, the mutual inductance between the two is given by mu naught N1 N2 pi R1 square L into basically your I2 is there, but that will also get cancelled, and what you will be left with only this much part. This much part is basically your mutual inductance, whichever you want over here. The same thing. This is your mutual inductance. Now, what is mu naught? Permeability. What is N1? Number of turns per unit length in the first coil. What is N2? Number of turns per unit length in the second coil, outer coil. Pi is pi. What is R1? R1 is the radius of the first coil. R1 is nothing but the radius of the first coil, the inner coil. L is nothing but the length of the coil. So that gives you the mutual inductance formula. Okay, that's something which you should know. Now going back to self-inductance. See, like I said, in self-inductance, you just have one coil, and in that coil, there will be some current, there will be some magnetic field produced by it. There will be some magnetic field produced by it. The changes in the current in that coil affects the coil itself. So here, the flux in that coil is proportional to the current. So that constant of proportionality, L, is called as the self-inductance of the coil. It's called as the self-inductance of the coil. I hope this is clear. Okay, Joker, hold on, bacha, concentrate on the class. The unit of self-inductance or mutual inductance is Henry only, standard. It's Henry. So if I ask you what is the unit of self or mutual, it will be basically 1 Henry, and 1 Henry will be 1 Weber upon 1 ampere. 1 Weber of flux created by 1 ampere of current. Now we all know by Faraday's law, rate of change of flux is EMF. So if you take the derivative of flux, what you get is this formula, which is L di by dt or M di by dt, depending on what you are using it for. So if the current changes, then the coil behaves like a battery, behaves like a EMF. The EMF produced by changing current in that coil is given by this formula, L di by dt if it's self-inductance. If it's mutual inductance, then it is M di by dt. Then it will be basically M di by dt if it is mutual inductance. Okay. Now you might be wondering why this negative sign is coming. Why this negative sign is coming? This is because of Lenz's law, nothing else. This is only because of Lenz's law, that whatever change in the current occurs is always opposed by the induced EMF. If current tries to increase, the EMF will try to oppose it. If current tries to fall down, the EMF will try to support it. That's the only reason why that negative sign is there. Keep this in mind. Okay, I hope this is clear. Understood? Very nice, very nice. Moving ahead now to AC circuits. Moving now to AC circuit slowly. In AC, standard things which you should know. Voltage and current both change with time. They are not constant. They first go this way, then they go other way. So if you write the mathematical equation, it will be either sine function or cos function. So Vm sine omega t will be voltage. Im sine omega t will be the current. Vm and Im are the maximum voltages that can come or currents can come. So it is also called as the amplitude of the voltage or amplitude of the current. Omega is nothing but your frequency angular wise. In fact, I can write omega as 2 pi into the frequency of the AC voltage. Vm and Im, these are nothing but your amplitudes of the voltages or the current, because every voltage or current will be like this. First positive, then negative. First positive, then negative. What is this positive and negative? It's just the direction. If it goes this way, I consider it positive. If it goes other way, I consider it negative. It just says the current keeps changing the direction. Then you have the RMS value of the voltage or the current. The RMS value of the voltage or the current is given by, the RMS value of the voltage or the current is always given by maximum value divided by root 2. Now 1 by root 2 is 0.707, useful formula, useful constant, useful number which you can remember. So guys, RMS is always the max by root 2. What is the meaning of RMS? The meaning of RMS is basically that current or that voltage which behaves like the DC equivalent. So imagine I have AC circuit. If I want to convert it into a DC circuit, so if some energy is getting lost across a resistor, if there is some power loss across a resistor, and in AC every time the voltage is changing, plus minus, zero, maximum. If I want to write it as one constant voltage which will give the same loss, which will behave the same way as that of that AC, then that constant DC current will be the RMS value. That is basically the RMS value. So the same constant current which has the same effect as that of the AC current or AC voltages to produce the same heat, to cause the same losses, to cause the same power dissipation in that particular circuit. Keep this in mind. Root means square. Also, keep this in mind. Vrms square is V1 square, V2 square, V3 square. All the voltages you square and add them upon the number of values that you have taken. Let's say n number of values, and put it under the root, just like your RMS speed in kinetic theory of gases. That is the meaning of RMS. Now, you will always see that in case of AC voltages, the currents and the voltages are not simultaneous. If one is sine, maybe other is cosine, or maybe other is sine only, but with a phase difference. They are not simultaneously occurring. So you can see over here, if the voltage graph is like this, the current graph might be slightly offset by some value. Then it is said that there is some kind of a phase-wise difference between the voltage and the current. There is often a diagram used called as the phasor diagram. This phasor diagram is just a diagram which is made in your head or on the paper, which represents the actual physical phenomena. This helps us understand who is ahead of whom. What is the difference in time? How much time does voltage take to reach the same value as that of the current? And also helps us to add the voltages, subtract the voltages, and play with them. So that is why you use something called as the phasor diagram, which is just a representation of the actual diagram. Keep this in mind. Okay, I hope this is clear. Now, if you take inductor, if you take then let's say capacitor, this is supposed to be capacitor, not inductor, guys. And if you take resistor, each time you will see one will be ahead of the other, or maybe in the same direction. Now, who is ahead, who is behind? I'll tell you a simple way. Forget the individual diagrams, forget the individual things. I'll tell you what you can do. In general, beat inductor, beat capacitor, beat resistor. Observe this carefully. Always remember, whenever you have an AC circuit connected to resistance, capacitance, and inductance, the same current will flow through all of them. It's the same current which flows through all of them. So in the phasor diagram, always show current as a common entity because it is the same thing across all of them. Now comes the resistance part. Resistance is always in the same phase as that of the current. There is no mismatch. The voltage and the current climb up and down simultaneously, so there is no lag between them. So if somebody happens to measure the voltage across the resistor, I will show it in the same direction as that of the current. So that's the usefulness of a phasor diagram. I immediately understand, oh, it's in sync or it is not in sync. Okay, I hope this is fine. Now what happens is, if I take an inductor and capacitor, the voltages are not in the same phase. If I measure the voltage across the inductor, it is not in the same phase. Across capacitor, it is not in the same phase. I hope you remember this. So if you want to remember who is ahead of whom by how much, simple rule. Remember the phrase, love is above all, right? Love is above everything else in the world. So VL is above everything, and obviously the remaining thing will be VC. Now treat them like vector quantities. Yes, like vectors. Like if you treat forces, one force here, one force here, one force here. Find the resultant force. So vector here in this case, that will give you the EMF applied over here. So that will be the net EMF applied over here. So this E vector is basically VL vector plus VC vector plus VR vector. Keep this in mind. It's a vector addition. That's the usefulness of your phasor diagrams. But if you look at the value, of the EMF, then it will be, understand, first take care of VL and VC. VL is on the top, VC is at the bottom. So the net vector will be VL minus VC, assuming VL is more. The only remaining vector is basically VR. So their resultant is basically EMF. So I can use Pythagoras. So it will be basically VR square plus VL minus VC whole square. But if you put bar, then this will be the formula. If you skip the bar, only talk about the magnitudes, then this is the formula. Is that okay, bacha log? Is that okay, bacha log? Excellent, excellent. Now, similarly, that we have talked about voltages and how they add using phasor diagrams. Is there a relationship between the voltage and the currents? The answer is yes. I'll tell you how. Like for example, this voltage VR is basically current into the resistance. The same current I into resistance is the voltage across this guy. VC will be also equal to current into resistance. VL will also be equal to current into resistance, but the resistance of capacitor and inductor is not R, it is something else. That equivalent is called as capacitive reactance or inductive reactance. So here you multiply it by XC, here you multiply it by XL. This is the equivalent of resistance for a capacitor or an inductor in AC circuits. Is that okay? Is that okay, bachalo? Everyone with me? So it's very similar and identical formulas. V is IR, V is IR, V is IR. V is over here I into X, here I into L. That's all, XC and XL. Now what is the formula in XL? I put it up in the previous slides. The capacitive reactance and the inductive reactance. Inductive reactance is omega L, angular frequency into inductance. Capacitive reactance is 1 by omega C. 1 by omega C. Omega is angular frequency, C is the capacitance. So now, looking at all these diagrams, you can never ever be confused. For an inductor, voltage is always ahead of the current by 90 degrees. For a capacitor, voltage is always behind the current by 90 degrees. Resistor's voltage is always in phase with the current. The net EMF might make certain angle, I do not know how much angle, but it will make certain angle, and that angle can be easily found. That is the total phase difference between the voltage and the current. So you can find tan phi. So you can see over here also this is phi. So tan phi will be opposite by adjacent. Opposite will be VL minus VC. Adjacent will be basically VR. So that's how you can find the total phase difference in that particular AC circuit. So using simple trigonometry, guys, geometry is the simple. So nothing great about it. So these are the main formulas which you should know in AC circuits for LCR series. Okay, I've put up all these things over here as well. The other diagrams look very confusing, but if you go by my diagram, it will look easy and you'll get marks also, don't worry. Now, there is a special case where you calculate the current in the circuit and you try to see when is that current maximum. Let's come to that. See, just like I said, V is IR, this V is IX, this V is also IX. This total voltage is also current, but this time it is called as impedance. Like numbers, X was a reactance, Z is basically your impedance. The formula for impedance is very similar to the voltage formula. So Z is basically root of VR. No, instead of that you just put R. R square plus XL minus XC whole square. That is the formula for something called as impedance, which is the total resistance of the AC circuit. It includes the resistances of resistor, capacitor and inductor equivalent in AC. So that is the total resistance of the circuit. Like you can see, for a given voltage, if I change XL or XC, current will change. If I change omega, I will see current will change because Z will change. So there is a current for which, or there is an angular frequency for which the current is maximum. The frequency is maximum. Then that current, when then that frequency when the current is maximum is said to be the resonant frequency. So you will see that happens when XL and XC both are equal to each other. You get something called as the resonant frequency. So in the phasor diagram, you will see both VL and VC are equal. VL and VC both are equal. So they cancel out each other. So the net voltage is equal to the EMF in the direction of the current. Both these vectors cancel out each other. So that's when you get maximum current. It is said to be resonating, and the impedance will just become the resistance because XL and XC just cancel out each other. Keep this in mind. These are certain important things which you should know in the case of LCR series circuit. If you draw the graph, actually it becomes very, very clear. If you draw the graph, it becomes very clear. Here your frequency is there, here current is there. The graph goes like this. Only at a particular frequency the current is maximum. Okay, so that is when it is resonating. Now what happens, guys, is that if you look at this graph, you see that the graph can be thin, it can be wide, it can be tall, it can be shallow. So there is a quantity called as the quality factor of the circuit. How sharp it is. If it's a sharp graph, thin, narrow graph, it has a good quality factor. If it is a wide graph, shallow one, then it has a bad quality factor. So quality factor is basically the sharpness of that current versus omega graph, and that formula is omega naught L by R. Omega naught is basically the resonant frequency, which is 1 by root LC, standard formula. This is your resonant frequency, 1 by root LC. So that resonant frequency into L by R gives me the sharpness of that curve, which is also called as the quality factor. Keep this in mind. Is that okay? Cool. Excellent. Now, just like a current flowing in a resistor causes heat loss, power loss, same way, if AC current also flows in the circuit, it will cause power loss. Just that the formulas look slightly different. Look over here. It is actually I square into Z into cos theta. You can also write it as voltage into the current into cos theta or cos phi, you can say. Voltage into current into cos phi. If you're wondering why am I writing it like this, because see, voltage and current don't go up and down together. There is always some phase difference. So that needs to be accounted for. So that is accounted by this term called as cos phi, which is nothing but the power factor. So the power factor accounts for the phase difference between the voltage and the current, because they are not going up and down together. And for a resonating circuit, you will see the power factor. The power factor is going to be 1. Basically, it's going to be maximum. It's going to be maximum current. So it causes maximum power delivery from the source to the LCR circuit. So that's when the power factor is 1 or phi is 0 basically. Keep this in mind. Okay. So cos phi. Okay. Sorry. This thing. This is different. So this is purely inductive or purely capacitive. This one, maximum power dissipation happens when cos phi is basically 1. This is basically your resonance. By chance, there is only inductor or capacitor, no resistor, then there is no question of heat loss. Phi will be either plus 90 or minus 90. Cos of 90 is 0. So you will see cos 90 will be 0. So then there will be no power loss. So there is no power loss only in the case of inductive or capacitive circuits. Only pure induction or pure capacitance or just a combination of capacitance and inductance, no loss. Only when resistors are there, you will see there will be power losses. Okay. So keep these things in mind. Great. Moving on to transformers. This is the last application of your EMI, where you will see that whenever you want to change the voltage, maybe you want to increase the voltage or you want to decrease the voltage, you will see that you will use the concept of mutual induction, where you can increase the voltage, but at the cost of decreasing the current. You can also decrease the voltage at the cost of increasing the current. So if you try to increase the voltage, it is called step up. If you try to decrease the voltage, it is called as step down. Now, in a transformer, basically you have 2 coils, and because it's a AC voltage or AC current, so the current keeps changing. That affects the other coil. It creates EMF in the other coil. So through mutual induction, EMF is generated in the secondary coil. Now it so happens that if you measure the voltage in the secondary coil divided by the voltage in the primary coil, it is exactly the same ratio as the number of turns in the secondary coil upon the number of turns in the primary coil. So Vs by Vp is Ns by Np. But like I told you, when you increase voltage, current reduces. That's why you will see the ratio of the current is exactly opposite. So Ip by Is is Vs by Vp. So very, very important. P by S, here S by P, S by P. So only for current, the ratio is opposite. Everything else is in the same order. Okay, keep this in mind. So that is basically the formula which I'm going to remember in case of transformers. Moving on to electromagnetic waves. Now, see guys, we saw that when you have current carrying wires, basically charges moving, it creates magnetic field. When you take magnets and move it in Faraday's law, it creates electricity. So electricity can create magnetism, magnetism can create electricity. So when you talk about light, X-rays, ultraviolet rays, radio waves, all these have a very similar thing in common. There is some similar thing. What is that similar thing? They both, or all these things have electricity in them as well as magnetism in them. Basically, they are electrical energies and magnetic energies which are flowing everywhere. So when I see red color, ultraviolet rays are there, Wi-Fi is there, radio waves are there, FM is there. They are all the same things. They have electrical and magnetic energies in equal amounts. In fact, the electrical field goes as a wave. The magnetic field also goes as a wave. That's how light propagates. And both these fields are perpendicular to each other as well as the direction of propagation. So if electric field is here, magnetic field is here, velocity of the wave is there. So both these waves go simultaneously in the 3D space around you. Keep this in mind. That is your electromagnetic wave. Standard formulas which you are supposed to remember. Any wave equation is of the form amplitude sine kx plus minus omega t. Same way over here, electric field will be electric field's amplitude into sine kx plus or minus, depending on whether it is going this way or that way. Doesn't matter whether you put minus or you put plus, it's the same thing. Okay, but if you put plus here, put plus here. If you put minus here, put minus here. Don't change it. And same way, magnetic field is also going to be like a wave. So it will be magnetic field amplitude into sine kx plus or minus omega t. Now, if you divide the electric field and magnetic field equation, sine and sine will cancel. So what you will be getting is E by B is E naught by B naught, and this quantity is the speed of light. This quantity is also called as the speed of light. Yep, very, very important formula. You should know this formula. The speed of light is electric field by magnetic field. Also, speed of light is frequency into wavelength. That's also standard. You can also remember this as 1 by root of mu into epsilon, mu naught into epsilon naught. All these things are related to the speed of light. Okay, so standard things related to electromagnetic waves and its equation. Remember, electromagnetic waves also carry energy. Yes, electric field is there, magnetic field is there, so obviously they will be carrying energy. And they will be also carrying momentum. Yep, although it is an electric field wave and magnetic field wave, it can apply a force when it hits a surface. So it definitely possesses momentum. So when it hits, it applies force. And if you measure this force and divide it by the area on which the force is acting, what you get is the force acting per unit area, which is nothing but the pressure. So the pressure of the wave, pressure of the light, pressure of the radiation around you is always felt, but it is very, very, very small. So that's why you do not get the sensation of it, but it is there. So the force provided by the light per unit area when it falls because of the momentum that light possesses is called as the radiation pressure. It's called as the radiation pressure. Keep this in mind. Okay, and the formula for that is nothing but U by C. U is the energy, P is the radiation pressure, C is the speed of light. Standard formula. Now this electromagnetic spectrum, I want you to remember all the terminologies and bifurcations, which is visible, which is infrared, which is ultraviolet. We should know the approximate range. So I have put this slide up for all of you. Longest one is the radio waves. Then you have AM waves. Then you have the short radio waves, FM waves and all that. Micro is smaller than that. Then comes infrared. Then even smaller wavelength is visible. There you have violet, indigo, blue, green, yellow, orange, red. And then you go to ultraviolet. Then you go to X-rays, even short wavelength, high frequency. And then the highest will be gamma rays. And then you have cosmic rays. So this order is very important. At least know the approximate range of few of the things. Maybe not the exact values, not needed, but few things at least you should know. Either know the frequency or know the wavelength. If you know the wavelength, you can find frequency. If you know frequency, you can find the wavelength. Okay, keep this in mind. Now, you should also know what are the uses and applications of each of them. So there is a beautiful table mentioned in your NCERT. Okay, radio waves, typical wavelength range. What is it or how is it produced? Using acceleration of charges in antennas. Aerials means antennas. It is also detected using antennas or aerials. Microwaves, infrared, light, ultraviolet, X-rays and gamma rays. Gamma rays, like you know from the chapter of nucleus, it's always produced in a nuclear reaction. X-rays are produced by heavy elements. You might have read in modern physics, Mosley's law and all of that. So heavy elements will produce X-rays by electron transitions from higher to lower energy orbits. Ultraviolet, light and infrared, they are all produced in general via normal electron transitions from different orbits. They jump, electrons jump from one shell to the other shell. How you get these kind of lights radiations. Microwave is produced using a Klystron wall or magnetron wall. You don't have to know the functioning of it, but just know the name. Okay, using a magnetron wall or a Klystron wall. Okay, these are some important things which you should know as a table. Okay, let's move ahead by taking a short break. Just give me 5 minutes. We will continue. Okay, just give me 5 minutes and then we are going to continue towards the last segment of the discussion. Just 5 minutes. Okay, we'll meet in 5 minutes. I'm back. I hope you guys can see me as well as hear me loud and clear. Let me know in the chat box. Ready for the last segment? No breaks after this. Full Josh, full energy. I want everyone full on energy because now there are going to be no breaks. I know I had planned it to be till 1:30 or 2 o'clock, but because we had that brief disruption, we had to extend it, and but that's okay. I think not more than 45 minutes or whatever. Okay, ready? Okay, let's gear up. Let's start with the last part. So the last few chapters are ray optics, modern physics, wave optics, and obviously semiconductors and all of that. So let's go straight away to ray optics now. In ray optics, the first important thing is regarding reflection. If they ask you laws of reflection, you will always put up 2 pointers. First point, angle of incidence is angle of reflection. All the angles are measured with the normal, and the incident, reflected, and the normal ray are in the same plane. That's with regards to your laws of reflection. The next thing is that the sign convention. See, whenever you write object distance, image height, etc., everything has a sign, plus minus. Everything is a coordinate at the end of the day. What is the correct way of writing it? A lot of people think right side is positive, left side is negative. That's not correct. In fact, whichever direction the light enters, incident, that direction is positive. So if light is coming down like this, then downwards is positive. If light is coming incident like this, then that side is positive. So the incident direction of light is the positive direction of light. Opposite will be negative, opposite to the incident light. So this side will be negative, that side will be positive. Be it a mirror, be it a lens, be it anything, combination of lens, mirror, doesn't matter. Always go with incident light only. No, I did not take my lunch. I will have my lunch only after this session is over. Okay. Next important thing, for curved mirrors. For curved mirrors, remember all these things are there important from your CBSE board point of view. You will see there are 2 kinds of mirrors. One is a concave mirror. This is a convex mirror. A concave mirror is also a converging mirror. A convex mirror is a diverging mirror because it spreads the rays. In case of a concave mirror, the rays meet at a particular point, which is called as the focus. In case of a diverging mirror, when the rays extended backwards, then they meet at a point called as the focus. This focal point is related to the radius of the curvature of the mirror. This mirror is actually a part. This mirror is actually a part of a big sphere, right? It's actually a big sphere. It's a part of that. So if you take the radius, that is called as the radius of curvature. If you make the center of that big sphere, that is your center of curvature. So your focal length is always radius of curvature divided by 2. Rather, I would say the focal point is the midpoint of center, and the pole. Pole is the center of the mirror. So the center of the mirror is called as the pole, and the midpoint of pole and the curvature center is the focal point. So that's why F is radius divided by 2. Next important formula is the mirror formula. If I tell you where the object is kept, and if I tell you what is the radius or the focal length, you can immediately find where is the image formed. No need to draw any kind of ray diagrams. So the formula is 1 by V plus 1 by U is 1 by F. That's the mirror formula. Very important. You can find everything. So in case you have forgotten, V is always your image distance. U is always your object distance. F is your focal length. You also can find the magnification. Like if this is the object, this is the image can be small, it can be erect, it can be inverted, it could be big, it could be same size. So how is the image reshaped? That is your magnification. It is the height of the image upon height of the object. The answer for the magnification, this is your magnification, this is your magnification, this small m, comes out to be minus v by u. V is your image distance, u is your object distance. So this is another important formula which you can keep in mind. Minus v by u. See guys, if m is positive, that means it is basically erect. If m is negative, that means it is inverted. That is something which you can keep in mind. If it is positive, it is erect. If it is negative, it is inverted. Okay. What is, mirror formula derivation? Yeah, you should go through it. You should go through it once, definitely. Okay. Now, what is the principal focus and secondary focus? That will be more important, Marsal. In case of lenses, in lenses, you have two focuses, primary focus and secondary focus. So I'll come to that in lenses. Just give me some time. In mirrors, you don't have secondary focus. You just have one focus, and that is also the primary focus. Okay. So in successive reflections, what you will do is that you keep changing the sign convention. If a mirror is there, again another mirror is there, the image of one is the object for the next. That guy's image is the object for next. That's what you will do, number one. Number two, if the direction of the incident ray changes, you will also change the sign convention. Okay, I hope this is clear. Awesome, awesome. Now, let's go to refraction also. If rays can get reflected, they can bounce, they can also go in the other medium, that is transmit. That phenomena is called as refraction. And you will see when the light rays transmit into another medium, they slightly bend either towards or away from the normal, depending on whether the medium is becoming dense or rare. If this is angle of incidence, this will be angle of refraction. Okay, this is angle of incidence, this is angle of refraction, always measured from the normal. You will see that the value of sine of I by sine of R for any change of medium, the angle of incidence is sine and the angle of refraction sine is a constant, that ratio is a constant, that is called as the refractive index of the medium with respect to the previous medium. So that is basically the refractive index of this medium 2 with respect to medium 1. That's what you call it. Okay, and this is also equal to 1 by n12. So if you change the order, you take a reciprocal. If you change the order, right, you take the reciprocal. You can also write this as refractive index of 2 upon refractive index of 1. So n21, 2 is first, right? So 2 comes on the top, 1 is later on, so 1 comes below. So all these are equivalent formulas, sometimes used for solving problems, because they will give you refractive index of glass, water. What is the refractive index of glass with respect to water? Angle of incidence is here, angle of refraction is how much. So for those kind of problems, you are going to need these formulas. Now, what happens is, guys, when light changes medium, let's say it goes from rare to dense, it bends towards the normal. But if it goes from dense to rare, it goes away from the normal. The problem happens beyond a certain limit of incidence that you cannot increase the angle because you no longer can refract the ray. Like, look over here. This is dense, this is rare. This ray can easily go out. This ray bends away. This ray bends even further away. This ray does not get a chance to bend away because that's it, it's bending at 90 degrees. If the angle of incidence is further increased, you will see it cannot go out, it will only get reflected. This phenomena is called as total internal reflection, TIR. This happens if the angle of incidence is more than or equal to the critical angle. Critical angle is that angle at which the ray grazes through the surface, or basically the total internal reflection just begins. That's the critical angle. And the sign of that critical angle is basically the, I would say, the refractive index of the rarer medium with respect to the denser medium. So instead of remembering this formula, instead of remembering this formula, I would say, remember like this. It is 1 upon refractive index of the dense medium with respect to the rare medium, or you can just write it as refractive index of the rare medium with respect to the dense medium. Remember, this number, when I talk about dense medium with respect to rare medium, this number will always be more than 1, like 2, 1.5, 1.33. So the reciprocal will always be less than 1, which is correct also, because whenever you find the sign of any number, it will always lie between -1 and +1. It cannot be more than 1. So 1 upon that will always be lesser than 1. That's why you put the big number below. Keep this in mind. Okay? Is that understood, guys? Everyone with me? Let's move ahead. If the medium changes, but while changing the medium, the surface is curved, then you use slightly different formula. See, these formulas are okay for flat surface refraction, flat surface refraction. The moment the surface is curved, here there is one medium, here there is another medium. So if you place an object here, the rays will bend and meet somewhere to form an image. This then is your pole. If the rays are going like this, then this will be positive side, this will be negative side. From the pole to here, this will be object distance. From the pole to where the rays meet is the image distance. Then to locate the image, use this formula, refractive index of second medium by the image distance is equal to, minus refractive index of the first medium upon the object distance, which is equal to difference of the refractive index by the radius of curvature. This is basically curved, so it will definitely have some kind of a radius. So this is the formula which you'll use for curved surface or spherical surface refraction. Very simple. Use sign convention. That's all. That's all. Okay. Now, using two surfaces, you can make a lens. Two surfaces, curved surfaces with a medium inside makes it a lens. So if you have two surfaces like this bulging out, it becomes convex. If you have two surfaces pressed inside, it becomes concave lens. Now convex lens is converging in nature. The rays which are parallel, they meet over here. In case of concave lens, the rays which come parallel, they spread out. That's why it's a diverging lens. If the rays come like this, they meet here, that is called as the primary focus. This is your primary focus. Understood? The rays actually will meet here. If the rays go like that, they diverge from this point. So this becomes your primary focus of the concave lens. Now, if the focus is there this side, obviously the focus will be there on the other side also. Same thing, focus will be there on the other side also. That other focus, same distance on the other side, is called as the secondary focus. So I'm just going to call this as the secondary focus. I'm just going to call this as the secondary focus. Keep this in mind. That's all. This is just your secondary focus. Okay, I hope this is clear. Everyone with me on this? Awesome, awesome. So somebody had asked this doubt also. Now, in order to find what is the focal length of any lens, all you need to tell me is what is the material inside and what is the radius 1 and radius 2 of the curved surfaces. So you have the lens maker formula, which is refractive index -1 into 1 by radius 1 minus 1 by radius 2. That gives me the focal length of that lens, focal length of that particular lens. Okay, that is why it is called as the lens maker formula. To make the lens, what do you need to give me? You need to give me the material, you need to give me the radius. So this is the principal. Primary is the principal focus, bacha. Okay, primary is the principal focus. Okay, Don't get confused. Primary, principal means the same thing. Secondary, auxiliary means the same thing. If I tell you where the object is, you can find the image using this formula. You can see this formula is very similar to mirror formula. The only difference is negative sign. In mirror, it was 1 by V plus 1 by U. Here it is 1 by V minus 1 by U. Magnification is also very similar, but the only difference is the sign again. In mirror, there was a minus sign, minus V by U. In lens, there is no minus, it is just plus V by U. Okay, so that's the major difference between lenses and mirrors. If you take the reciprocal of focal length, you get the power. Power is the degree of divergence or convergence. So if it converges, it's positive power. It's positive power. If it diverges, then it is basically negative power. If it converges very soon, it has good positive power. If it diverges very easily, it has good negative power. And it is reciprocal of the focal length. Remember, if focal length is expressed in meters, then only you express the power in diopters. Then only you express the power in diopters. Okay, understood, guys? Keep this in mind. Okay, so power is 1 by F. Now, if you think about it, for a convex lens, what happens is the focal length is basically positive. So the power also is positive. Whereas for a concave lens, what happens is that the focal length is negative. So the power is also negative. Keep this in mind. Okay, simple facts. What happens when you have multiple lenses, one after the other, sticking each other? Each lens will add to the power of the previous lens. So their powers get added. And since power is reciprocal of focal length, so their reciprocals of focal lengths get added. So whenever thin lenses are in combination, add their powers, not their focal length. Keep this in mind. Their powers get added. Focal length, in fact, reduces because it becomes more powerful. The rays can converge even sooner. So that's why it's a reciprocal of focal lengths. Going to prisms. Yeah, you can put up your doubts maybe towards the end of the class, maybe in the comment section too. Just keep following whatever I'm saying, bacha, for now. Okay, great. When you have a prism, the two surfaces where the refraction occurs is called as the refracting surfaces. Refracting surfaces. They are called as the refracting surfaces. The angle between them is the angle of prism or the angle of refracting or the angle of refraction of the prisms or the refracting angle of the prisms, whatever you want to call it. So this A is nothing but your angle of prism, angle of the prism. You will see that the ray enters at an angle I, it will refract at angle R1, it will be incident at an angle R2, and it will emerge out at an angle E. You can see the ray which was going here deviates by certain amount, delta. So the deviation in the ray which is produced is given by I plus E minus A. I is the incident angle, E is the emergent angle, and A is the angle of the prism. Keep this in mind. Okay, very, very important. Now, if by chance you want minimum deviation, then here is the condition, guys, for it. So for basically minimum deviation, so I will call the symbol delta m or dm, you will see incident angle and the emergent angle both are equal. So the rays are symmetric. I will be equal to E. In fact, R1 will be also equal to R2. Very important. In such a case, you will see the angle of deviation is 2I minus A. Angle of deviation will be 2I minus A because I and E both are equal, so it will become 2I minus A. As simple as that. And the refractive index of the prism becomes sine A plus minimum deviation by 2 upon sine of A by 2. This is only true for minimum deviation. Don't use this formula, otherwise you will get wrong answers. Very important. This formula becomes this formula if it's a very small or a thin prism. So if you have a very thin kind of a prism where the angle A is very, very small, then this sine becomes approximately equal to theta, and solving this further, you get this particular formula. This is only true for thin prism. The deviation angle is refractive index minus 1 into the angle of prism. Okay, this is only and only true for thin prisms. Please bear that in mind. This is true only for minimum deviation. Refractive index is sine A plus D by 2 upon sine A by 2. This is the general formula. In fact, I can give you one more formula over here. That is R1 and R2 are related to A. So you can also write R1 plus R2 is equal to the angle of prism. That is also a general formula. Moving ahead to the optical instruments formula. Yes, coming to optical instruments formula. Yes, it's easy, right? Very good, very good. First one is the simple microscope. See, you use optical instruments to basically improve the angle at which the image is formed. So if I see the object close, then the angle at which I see that image of that object is very large, so I can see it very clearly. So when I get my phone very close, I can see everything on the phone clearly. But there is always a least distance of distinct vision below which I can't see things clearly. Eyes are going to face a lot of trouble and strain to focus. That distance is called D, which is usually 25 centimeters for an average human being. So if you bring closer than that, you will start feeling a lot of pressure and you will not be able to focus. So that is least distance of distinct vision. For a normal human being, you can focus till infinity. That means you can see a distant star or a mountain very easily. Only when you have defects, then that far point and the near point change. So the far point might come closer. So maybe only till 10 meters you can see things clearly. Beyond that you can't. Or it can be opposite also. Maybe you cannot see things closer than 1 meter. Actually, you should be able to see till 25 centimeters, but maybe you cannot see anything before 1 meter only. So these are the problems which arise because of the defects in your eyes. Now, you can use instruments to amplify the size of the image. The first one is the simple microscope. The magnifying power of a simple microscope, how many times is the image as compared to the object angle-wise, is given by 1 plus D by F if it is in the least distance of distinct vision situation. This is only true for least distance of distinct vision. Remember, this D over here is 25 centimeters on an average. This F is the focal length. This is the focal length of your lens, basically a convex lens. You just use a magnifying glass. You can see the things become big. So the magnifying power is 1 plus D by F if you make the image form very close to the eye. If the image is far away, that means for normal vision, that is basically relaxed eye. So for relaxed condition, basically also called as the normal vision, then you do not put this one, is just D by F. You can see when you put in that additional effort, you strain your eye, you get a better magnifying power. When you relax your eye, then your magnifying power reduces. So that's one thing which you should know. Oh my God, why does it keep going out? Just 1 second, guys. Let me get it back. Yeah. Okay, I hope this is fine. Sir, distinct vision के लिए है ना ये सिर्फ no, you have it for both self, है ना, both distinct vision as well as relaxed. Similarly, for a microscope is basically a combination of two lenses, okay, two convex lenses. The first lens creates an inverted magnified image. The second lens behaves like a simple microscope, magnifying that image, creating a virtual inverted image eventually magnified. If you have normal vision, that means relaxed condition. If you use relaxed condition, basically that is normal vision, then use this formula, L by F naught into D by Fe. What is F naught and Fe? This is objective, right? Objective means close to the object, the focal length of the objective. Fe is where you are going to put your eyepiece. So the focal length of the eyepiece. D is 25 centimeters. L is basically the length of the tube, length of the microscope, which is from objective to the eyepiece. Whatever is the distance, that is the length of the tube. That is the formula that you're going to use for basically your normal vision. If by chance they give you for least distance of distinct vision, then just put 1 plus D by Fe. That's all. Nothing else will change. So the magnification here for relaxed is this much. For least distance of distinct vision, when you strain your eyes, the only term which will change is this term. It will be 1 plus D by focal length of the eyepiece. That's all. That's it. That is going to change. Now, why is this multiplication? Is because there are two lenses. This lens magnifies separately, number one. Second is this lens also magnifies this image again separately. So the total magnification is magnification by the objective and magnification by the eyepiece. So that's why you see the product. This magnifies 2 times, that magnifies 5 times. So total will be 2 into 5, not 2 plus 5. Is that okay, Bhadra, Nair? All right, moving on to the next one. If it's a telescope used for seeing faraway objects, then the magnifying power is very simple. It is just the objective's focal length upon the eyepiece's focal length. So magnification is simply put F naught by Fe. Also bear in mind the value of F naught and Fe together give you the length of the tube. Here the length of the tube is basically this one. From objective to eyepiece, F naught plus Fe is the length of the telescope tube. These are the formulas for telescope. Moving on to the next chapter, that's light waves. Coming on to light waves, guys. Let's move ahead. Yep. So can we expect problems from optical instruments? Yes, definitely. You can. Okay, cool. Moving on to the next one. In light waves, the first thing that you should remember is the Huygens principle and the Huygens construction. All points in a medium, okay, are oscillating in phase because they are at the same distance from the source. Such collection of points is called as a wavefront. So you should first of all know what is the meaning of a wavefront if they ask you to define it. So all the points which are at the same distance, they have vibrations simultaneously occurring. So they are basically called as the wavefront. Each source produces wavefronts around it, and these wavefronts grow in size. You can have a spherical wavefront produced by a sphere, or if there is a line source, it will produce cylinders which expand. If there is a plane source of light, it will produce planar source of wavefront. So you can have different shapes and sizes of wavefronts, and they keep growing as light moves ahead. How do I find these wavefronts? You can use Huygens construction. So go through Huygens construction once. Okay. So take a primary wavefront and then draw arcs or circles in the forward direction of radius equal to ct. Draw a common tangent. That common tangent gives you the new wavefront after time t. So you should know the Huygens construction. Is that okay? Cool. Moving ahead. If you move relative to light, you will see that the frequency of the light changes. Just like in sound, if you are moving relative to the source, you will see the frequency produced and what you hear are slightly different. That effect where you hear a slightly different frequency is called the Doppler effect in sound. Same way in light, if you move relative to light, you will see that the light is seen slightly differently. So blue color might look like violet color, or a red color might look like yellow color. That is only because you are moving relative to the light. That is called as Doppler effect in light. So the source might be producing one frequency. You might be seeing a difference in the frequency because of the velocity. This is the speed with which you travel. This is the speed of your travel. This is obviously 3 into 10 to the power 8 meters per second. This is your actual frequency. This is your actual frequency of light. This is the change in the frequency. Change in the frequency. So you can have some questions based on this as well. So the change upon the original frequency is speed by the speed of light with a negative sign. So if the if you are going away, like you can see, then what will happen is that this number will become negative and you will get a frequency smaller than the original frequency. If you come towards, then this V will be negative, negative into negative will be positive, so the frequency will increase. So keep this in mind, that if you are going away, then V is positive. If you are going towards the source, then it is negative. Accordingly, you will see whether delta is positive or negative, whether it should increase or decrease. That's all. Okay, keep this in mind. Now, when you have light waves and not just one source but multiple sources, each source will produce waves. They will all meet together. That causes interference. Each wave might have its own amplitude, its own intensity, and when they meet, the new wave will have a new intensity, which is also called as the resultant intensity, and a new amplitude, which is the resultant amplitude. Now, how do I find that out? First is, you should know where are you meeting. From this source I am meeting here, from this source I am meeting here, this wave travels like this wave travels like this. This wave goes this way, this wave goes this way. The difference of their paths, this is the path of each waves. The difference of the length of the path is called as the path difference. It's called as the path difference. So this quantity that you see over here is also called as the path difference of the waves. If that happens to be n times the wavelength of the waves, then you will see all the crests meet together, all the troughs meet together, and it will make a bigger crest and a bigger trough. That is called as a constructive interference. That is called as a constructive interference. Whereas if the difference of the path, is odd times lambda by 2, because you can see 2n plus 1 is odd number. If you take LCM, 2n plus 1 odd by 2 lambda, then it will be destructive interference, meaning the crest of this guy will come with the trough of this guy. The trough of this guy will come with the crest of this guy. They will cancel out each other. In any case, you can find the resultant intensity. So this is the formula for your resultant intensity. This I naught is intensity of any one wave. This phi is your phase difference. You can also find it like this. Delta phi is 2 pi by lambda into delta x. This delta x is your path difference. The same thing which I mentioned here. So if I know the path difference, I can find the phase difference. If I know the phase difference, using this formula, I can find the resultant intensity of light, sound, whichever wave I'm talking about. Yes. Okay. I hope this is clear. So these are the main formulas for interference: constructively, destructively. For constructive, n lambda. For destructive, odd lambda by 2. Intensity resultant is 4 original intensity cos square phase difference by 2, where phase difference is 2 pi by lambda into path difference, the difference of their path lengths. Now you can create this interference and form a beautiful pattern, and this setup is elaborately given by Young. He performed the experiment to show that light can interfere, hence it is a wave. So that is called as the Young's double slit experiment, where you take a source of light, you make it fall on 2 small holes or slits. From those 2 holes, they will behave like new sources. They will emit new wavefronts. They will spread in all the directions. Now these wavefronts from these 2 sources meet on the screen to produce constructive, that means bright regions, or destructive, that means dark regions. So you will see fringes, bands of bright and dark, That pattern is called as the YDSE pattern, Young's double slit experiment pattern. Okay. Now what happens is, from one fringe to the other fringe, from one bright region to the other bright region, or from one dark to the other dark, the distance is called as the fringe width, and that is given by lambda d by d. Capital D is the distance from the slit to the screen, whereas small d is the distance between the slits, Keep this in mind. Another important thing is that where do you get the bright fringe? Where do you get the dark fringe? Look at this. This formula is for bright fringes. You use n times this thing, lambda d by d. N is any integer. The first bright fringe, 1 lambda d by d. Fifth bright fringe, 5 lambda d by d. Whereas for dark fringes, use this formula, n plus half lambda d by d. Same thing over here. So first dark fringe, 1 plus half lambda d by d. That's how you can find the dark fringes. Is that okay? But n actually starts from 0 over here. So be careful. Actually, if you are finding first dark fringe, you put n as 0. Okay, so that's one other thing that you should be keeping in mind. Now, there were people who thought if two slits can create interference, can only one slit also create interference? The outcome was yes. So then people wondered, why does this happen? Then they realized actually what is happening is, even if you have one slit, in that small area, you have many points. And when the light enters and gets blocked and only a small portion of the light passes, each point in that gap behaves like a source. So in fact, there are many sources over here, each producing their own wavefronts. So instead of having one source, technically, in fact, you have infinite sources producing many waves, and all these waves go around in this space and interfere with each other. That phenomena of spreading of light, when it passes through a hole, aperture, or a slit, and it spreads, that is called as diffraction. You will see that when light diffracts, then also it forms a pattern. You will see a maxima, then dark fringe, then maximum brightness, and then dark fringe. But usually you hardly see 2 or 3 fringes only. After that it dies out. But yes, there is a pattern which is formed on the screen. And the formula for locating any of the fringe is given by this. So here, this formula is specifically meant to locate your first minima. The intensity falls as you go from one maxima to one minima. This is the formula which you are going to use for locating the first minima, or basically dark fringe. This one over here, or this one over here. This is the angle at which you are going to get the minima. So very important. I'll just probably put it in a different color. So just once again, this one. This is basically theta, where you get your first minima. Okay, this is basically your theta, where you get your first minima. Okay. Yes, bright and dark both have different formulas for YDSE, but in diffraction pattern, you should just know the formula for the first minima. That is more than enough. They are not going to ask you maximas and so much. Okay, very important. Now, slowly going to modern physics, guys. We are coming to the last segment. I hope you guys are still active. I know you guys might be hungry. Maybe some of you might have also eaten your lunch as you're watching this class. And if you had your lunch, just put up maybe some food emoji on the chat box. And if you're hungry, just put up maybe a smiley in the chat box so that we all can smile, because even I'm going to smile because even I am hungry. I know even I'm hungry, but that's okay. I'm going to focus on studies. So this is what, dedication is. This is how concentration is built up. This is how you motivate yourself and push yourself. You feel like it is not possible, but you say to yourself, no, I'm going to do it. You feel like giving up, you say, no, I'm going to do it because others are doing it, because my teacher is doing it. Okay, great. Some of you had liquids, some juices maybe. Awesome. Great, great. Chalo, let's move on now to the last few things. Hunger, concentration. Yes, let's do this, guys. Come on. Okay. Going to modern physics, talking about electron emissions, because we are going to go to photoelectric effect now. Electrons can be emitted by 3 ways. Very important question asked many times. Mark it, guys. Electron can be emitted by 3 different ways. Okay, so let's have a look at it. There is a certain amount of energy which is required to take out an electron from any object or metal. This energy required to take that electron out is called as the work function of the metal. Standard thing. And you should know the formula for work function also. That's the minimum energy required for taking it out. The formula for work function is H into F naught. This is basically your critical, or basically you can also call it as the threshold frequency. Just one second. This is also called as critical or your threshold frequency. H is your Planck's constant, so it is basically 6.6 into 10 to the power minus 34 Planck's constant. So this tells me how much energy is required to pluck that electron out of that solid. They are not going to come out readily. You can't just ask him, hey, come out. It's not going to come out. You need to put in some effort. That is the energy that is called as a work function. Now, how do you give this energy? It's up to you. There are 3 different ways. First one, thermionic emission. Thermal. That means temperature, that means heat. So you heat that body. If you heat that body, what will happen? There will be collisions. The atoms will move left and right, top, bottom. They will knock out the electrons. So the heat energy is utilized in knocking the electrons. That is what is thermionic emission. Field emission. You apply a strong electric field. We know electrons are charges, so they will get affected by electric field. So if you create a strong field by applying a suitable potential difference, that field will pull that electron out, and that's how you get field emission. The third one is photoelectric emission. In photoelectric emission, what happens is the energy from light is utilized to knock that electron out, and then you see the electrons getting knocked out with certain energy. That is photoelectric emission. So we are going to concentrate on photoelectric emission, but remember field emission and thermionic emission is also there. It can be asked as explain the different phenomena. You're going to write this entire paragraph as it is. Don't even miss one word from this, okay? Everything as it is. Now, what is photoelectric effect? I've just explained it to you. When light of sufficient frequency falls on a surface, then the energy of light gets utilized in plucking out that electron, and the electrons get knocked out. Those electrons are called as photoelectrons, and the effect is called as photoelectric effect. See how beautifully I'm writing it or explaining it or telling it to you. That's how you're going to write it in the exam also. Yep. So we're going to solve PYQs on day 3. What is tomorrow, guys? You know it, right? I hope you have not forgotten. Yeah, tomorrow is going to be 100 questions. 100 questions, assertion, reason, and your basically case study based. Everything, yeah, tomorrow. So in photoelectric effect, you will see that the number of photons emitted is directly proportional to the intensity of the light. The number of photoelectrons, the photoelectrons which come out, is dependent on the intensity of light. Why is that so? Because if light is more intense, that means more photons are falling. If more photons strike the surface, more electrons will get knocked out. No? Simple. That's the reason for that. So that's why as intensity of light increases, you will see the current or the electrons number will also increase proportionately, as you can see over here. Great. Next important thing. Now, when the electrons get knocked out, you might want to stop them and you want to see how much energy they have. That energy required to stop them is measured in terms of stopping potential. So these electrons are coming, you apply a reverse voltage and you retard the electrons, and you prevent them from reaching the other side. That voltage which stops the photoelectric effect, which stops the current, is called as the reverse voltage or the stopping voltage, stopping potential. So this stopping potential is going to stop the photocurrent. The photocurrent becomes zero. That is stopping potential. Keep this in mind. You can see that right over here. This is the current, this is the voltage. If you apply negative voltage, you can see the current reduces and becomes zero. If you apply forward voltage, the current increases but not beyond a certain limit, it gets saturated. So it's very important to see that the current also gets saturated. Very, very important, because after a point, even if you apply more voltage, no point, because only certain number of electrons are coming out. So increasing the voltage beyond a point has no effect, it just saturates it. You will also see one interesting thing. Even if I change the intensity of the light, the stopping potential does not change. Okay, because just changing intensity means changing the number of photons, means changing the number of electrons. But that does not change the fact that each electron still has the same energy. Increasing the number of electrons is one thing, changing the energy of each electron is other thing. So when you change intensity, you're just changing the number of electrons coming out or ejected out. But the energy of the electrons are still the same. So to stop them, I'm going to require the same amount of stopping potential. Is that okay, bachalo? Perfect, perfect. That's very important. Now you have one more important formula, which is also your Einstein's photoelectric equation. Maximum energy is h nu minus phi naught. But if you don't like this, I'll give you a better way of looking at it. Energy of the photon goes into two things. One is the work function, and the second thing is the kinetic energy. So if I give 100 joules, maybe 30 joules is required to extract it out, to eject it out. The remaining 70 will be there with the electron as kinetic energy. So energy of the photon is h nu or hf. Work function, you can call it as hf naught or just phi. And this is kinetic energy, so you can just leave it as kinetic energy. So you can rearrange this and you can get this formula also. Kinetic energy is h nu minus phi. Also remember, kinetic energy is measured in terms of stopping potential. So technically speaking, h nu is equal to hf naught or h nu naught, whichever formula you want to use. If you are using f, stick with f. If you are using nu, stick with nu. Usually I use f in physics because v gets confused with speed. That's the reason why sometimes you will see physics teachers using f symbol. Okay, kinetic energy is electron charge into the stopping voltage, Vs. What is this Vs? This is your stopping potential. This is nothing but your stopping potential. This is also an important formula. So keep these things in mind. Just blocking this for all of you. Either this or this or this. One is the same thing. From here you can go here. From here you can come down here. It's up to you how you want to proceed. Now, different properties of light and basically photons. There is a paragraph given in your NCERT. By heart each and every one of them. They can give you just maybe a question. What are the different properties of photon? List at least 4 or 5. If it's a 5-mark question or 4-mark question, they might give you this. All the points. For each point, you might get half a mark or 1 mark. Depends on the length of the question. Okay, or the marks of the question. So you have to mention that when light interacts with matter, then that light or that radiation behaves as if it is made of particles. Those particles of light are called as photons. So the interaction is very important. The particles of light is called as photons. That's the first point. Second point, each photon has an energy h nu. The energy of each photon is h nu. These are small packets, and the momentum is h nu by c, or energy by c. You can see that. You can also write it as h by lambda, one and the same thing. Each photon has momentum and energy. Okay, keep this in mind. First pointer was what is the meaning of photon. Second pointer is what is the energy, what is the momentum. Third point, all the particles of certain frequency or wavelength have the same energy. All photons of the particular wavelength or frequency have the same energy no matter where you look, and also the same momentum. They also have the same momentum. Now when you change the intensity of light, then what happens is that you will see that if you make it more intense, it's just that the number of photons increases. If you make the light faint, dim, then it's the number of photons which reduce. So when you increase the intensity of light, then it's the number of photons which are crossing will basically increase. So that's what will happen. So there is an increase in the number of photons if you increase the intensity. If you decrease the intensity, the number of photons will also decrease. So intensity is directly proportional to the number of photons which are coming out of it. Next one, photons are neutral. Obviously, there is no charge. They will obviously not get affected by electric or magnetic fields. So that is another important point mentioned over here. Also, when a photon hits an electron or a proton or an atom, you will see that all the energy and the momentum is conserved, but a photon might actually get absorbed or might get released. Like when you have atom and the electron goes from high energy to low energy, suddenly you get light, photon. Where did this photon come from? Magically, right? So that's magic. It's not conservation of photons. Similarly, if a photon hits an electron, it will get absorbed and the electron will jump to higher orbit. So photon is destroyed and it is converted into energy. So energy is conserved. Even if it hits the atom, the momentum will be conserved. The atom will start moving, but the number of photons is not conserved. So this is also another important point which you should know. Remember, especially in case of collision, it's the energy and the momentum which is conserved. But what is not be conserved is basically the number of photons. Is the number of photons which may not be conserved. Okay, keep this in mind. Okay, I've already made a session on derivations, bacha. I don't know whether you have seen this before. If you are watching this channel, right, I'll tell you what you can do. Just search for derivations. Just search for derivations, right? I think you'll get the answer. Yeah, see this. Handwritten derivations, current, electricity, moving charges, magnetism, Shreyas Sir. Handwritten derivations, electrostatics, Gauss law, capacitors. So all the derivations which are there, I have done it over here. You can just search for it. These are beautiful lectures for all of you just for derivation's sake. Okay, I hope that helps. Great. Moving to the next point. Just like I said in the previous slide, that when light interacts with matter, it behaves like a particle. So then people thought, can particles also behave like wave? The answer is yes. Particles won't behave like light. Particles will behave like wave. That wave nature of a matter, a mass, is called as the matter wave. So a moving particle, a moving matter produces something called as matter waves, just like this particle of mass m moving with speed v has an equivalent wave associated with it and some wavelength is there. That is your matter wave. The wavelength is given by Planck's constant by the momentum. This is one of the first formulas which you should know, also called as the de Broglie's wavelength of a moving particle. De Broglie's wavelength of a moving particle. Yes, diagrams must be drawn by pencil or pen. Use pencil only. Who is that? Pamarti. Sunanda, please use pencil. Don't use pen. Pen, you can use it for probably labeling some alphabets, but avoid that also. Preferably use pencil only. Okay, cool. Next, this momentum can also be found using this formula. Sometimes they give you that a charged particle is accelerated by a voltage difference and it gains some kinetic energy. In those cases, use this formula. Very, very useful. So what is this formula for? This is momentum. This is your momentum. Okay. This is your kinetic energy. This is the potential difference of the acceleration of the charges. So if you take a charge and accelerate by voltage, you will see it will acquire some kinetic energy as well as some momentum. you can directly use these formulas for those kind of questions. Keep this in mind. Now, also, you will see one principle called as the Heisenberg's uncertainty principle, which is basically to tell you that, listen, people, that you cannot actually see a particle at a place and know its momentum. Or if you know where the particle is going, you cannot know where it actually is. There is always a game of probabilities. So basically, Heisenberg said particle's position and its direction and its momentum basically cannot be known accurately. There will be always some uncertainty, and the error in position into error in the momentum is basically h by 2 pi. Okay, more than or equal to basically h by 2 pi. So that's how it usually is. Keep this in mind. Is that okay? Great, great, great. Yeah, Sandy, the live is going on, bacha. Live is going on. Okay. Now, since we are talking about photons, we have talked about de Broglie, matter and waves. The next concept is basically the different atomic theories. First one was by Thomson, then Rutherford, and then Bohr's model and all of that. So Rutherford experiment, diagram, and the concept of approaching distance should be well understood. You should definitely go through the textbook. So you will see things like there is a source of alpha particle, it passes through a slit and hits a gold foil. Most of the rays go undeviated, some rays deviate by small angle, very few rays turn back and hit on the opposite side. That's because the nucleus is very dense and positive charged, and even alpha particles are positively charged. Most of the atom is empty, that's why all the particles go through the gold foil. That led him to believe the model of the atom should be such that there is a strong positive charge at the center of the atom. All the mass is over there. Most of the atom is empty, and the teeny mini negative particles just go around that positive charge. And if you look at the paths taken by different alpha particles, you will see most of them will go undeviated. Some of them come very close and then they go far away. Some of them which are targeted on the nucleus, very few of them will get deviated 180 degrees. So this B is also called as that impact parameter, wherein that decides how much angle will it get deviated by. If the path is slightly offset by some amount, then you will see the deviation is less. As the impact parameter reduces, you will see that the closest distance of approach also decreases, and closest distance means till where does the alpha particle come, as close as possible to the nucleus. And you will see that as this parameter reduces, you will see it will have an increase in the deflection angle. Is that okay? Yep, that's how it's going to go on. Okay, so this is very important. Now, the next model is basically your model of Bohr, which is used to find the radius or the speed or the energy. The derivations you should know. Main thing you should also know is the final formula. What is it proportional to? Like, for example, if I tell you radius is proportional to n square by z. Velocity is proportional to z by n. Energy is proportional to nothing but z square by n square. You should know this at least. So when you derive, you know for sure that you have done it properly. Z is atomic number, n is principal quantum number. Okay, at least know this much. That is very, very important. And yes, keep one thing in mind, especially with regards to energy. The total energy is kinetic energy plus potential energy, and the kinetic energy basically is nothing but, I can say, negative of the total energy, and the potential energy is nothing but yes, it's nothing but twice of the total energy. So if you know these two things, it helps you solve many questions as well. Okay, not just here, but even in JEE and NEET you will see that. So keep these things in mind. This total energy which comes out, it comes out as minus 13.6 Z square by N square in electron volt. Okay, so you don't have to remember these things, that's useless. It can be asked as derivation. You just derive it properly, and get the final form. You should know what is the final form, what is it dependent on, who is it proportional to, is it square or is it z or whatever, or inversely related to. That's it. That's all you should know. If you know that, rest derivation is very simple. Now, because there are different energy levels, and when the electrons go from one shell to the another shell, one orbit to the another orbit, what happens is that you will see certain wavelengths of photons only are involved. Like if it goes from fourth shell to first shell, a certain wavelength is emitted. If it goes from third shell to second shell, a certain wavelength is emitted. So these wavelengths are clubbed together because they are very close in value, and of a bigger spectrum of wavelengths, you will see that when the transition happens from some orbit to a particular orbit, all these wavelengths come together close enough, and you can attribute them to the person who found it. The person who found all these lines of wavelength for a certain transition is Lyman, then you have Balmer, and then Paschen and Pfund and Brackett and all of that. So what are these different series? So if, remember guys, I show the energy levels like this. If the transition happens from here to here, oops, 1 second. This is n is equal to 1, this is 2, this is 3, this is 4, this is 5, and so on and so forth. These are energy levels. If the transition happens from here to here, this is basically your Lyman series from 2 to 1. Then you have basically your, this is Lyman series. Anything comes to your, what do you say, first shell, that is your Lyman series. Then here, if you get transitions like this, okay, that is called as Balmer series. Similarly, if you get transitions like this, Lyman, Balmer, and then you have Paschen series. That's what these series are, depending on where the transitions are happening. So from any shell, if Lyman. From any shell, if it comes to second shell, it's Balmer. From any higher shell to third shell, it is Paschen, and so on and so forth. Is that okay, bachalo? Everyone? So there is a formula for finding the wavelength also. Now I have put the formula, substituted it, and shown it to you. But in general, the wavelength formula is R atomic number square 1 by n1 square minus 1 by n2 square. For hydrogen, Z is 1, so ignore. If it is helium, put it as 2. This is 1 by the wavelength, is Rydberg's constant, 1 by first orbit, and this is n2, which is the second orbit. Like you can put 4, 3. For Balmer, you can put like 3, 2, or 5, 2, or 4, 2, whatever you want to put. So accordingly, you substitute the values of n1 and n2. R is nothing but your Rydberg's constant. That's the formula which you can remember. Everyone with me? Yep. I don't think there should be any lag, bacha log. Okay, moving ahead. In Bohr's model, please remember that they can ask you what are the postulates of Bohr's model and derive the formula for radius, or explain the postulates and derive the formula for velocity. These kind of questions can come, I'm telling you. So what are the postulates? Number 1, the first postulate, just showing it to you guys, is that atoms revolves in an atom, the electron revolves in certain stable orbits and there is no emission of energy. That's the first postulate. Then the next important point that you should know is that each atom has definite stable states in which it can exist, and that state has fixed amount of energy. These are called as the stationary states of the atom. Only in certain states it can exist. It cannot be in between of them. Either this or that or this. Nothing in between. These are your quantum level phenomena. Next, it says that in these orbits, the electron which revolves around the nucleus has a specific angular momentum in integral multiples of h by 2 pi. So the angular momentum is nh by 2 pi. Angular momentum is n times, n is any integer, principal quantum number basically, Planck's constant divided by 2 pi. Only these angular momentums are allowed. So you can say the angular momentum is quantized, only certain quantities are allowed. Next important parameter is that in Bohr's model, we assume that electron might go from one shell to the other shell, or from higher shell to lower shell. Transition can occur. The electron might make transition from one state to the other state, and when such a thing happens, it basically emits or absorbs the photon. And the difference of the energy goes in the difference of the energy of the levels goes into the energy of that photon. Like over here. If it goes from 5 to 3, there is energy here, there is energy here. The difference of the energy is the energy of the photon. That's what the next postulate is all about. From this only you can find anything else. Okay, keep this in mind. Everyone cool? Let's move on. I think this energy levels, I mentioned this to you. So the lowest energy is the ground state. Then you have the first excited state, second excited state, third excited state, and so on and so forth. And after a few lines, you will see the electron is not even attached to the atom. It's basically unbounded. It's free. And if the electron reaches here, the atom will get ionized. So if you send an electron from here to here, you can say the atom is ionized. And the energy required to do that is also called as the ionization energy. If you take the electron from here to here, then you need some energy, but not so much. That energy is called as the excitation energy. This will be the first excitation energy, this will be the second excitation energy, and so on and so forth. So you should know what is the meaning of ionization energy and also excitation energy. Was that okay? And I think I gave you all these things, Lyman, Balmer, Paschen, in one of the previous slides as well. Limitations of Bohr's model, you should know it. They can tell you, explain the postulates of Bohr's model, and also state 2 limitations of Bohr's model. Or what is Rutherford's experiment, and what were the limitations of Rutherford's experiment, and how did Bohr overcome it? It can be a good 3 to 4 mark question, remember that. So Bohr's model is applicable to hydrogen atoms, but it cannot be extended to even 2 electron atoms like helium. First disadvantage, you can see that over here. In fact, also the difficulty lies because the electrons interact with each other and you neglect those effects in case of the Bohr's derivation. Also, if you use Bohr's model and find out the wavelengths which are emitted when electrons transit, and you place such things in magnetic fields, and you place some these things in magnetic fields, you will see, I don't know whether it's mentioned over here. Okay, I don't think it's not there over here. Yeah, so you will see that these wavelengths begin to split into magnetic fields when they are placed over there. This effect is called as the Zeeman effect. Bohr's model was not able to explain the Zeeman effect, which is basically splitting off the wavelength, splitting of these lines, spectral lines, under the influence of magnetic fields. So that is one more thing. I have not put it over here, but it is there. Okay. Another thing is, although it predicts frequencies by hydrogen atom, it is unable to explain the relative intensities of frequency in a spectrum. Why certain wavelengths are more, why certain wavelengths are less. That relative changes in intensity was not being predicted by Bohr. So that's the limitation of Bohr's model. It also did not take into account Heisenberg's uncertainty principle. That is another disadvantage of Bohr's model. No thing can be located precisely. Radius and velocity, impossible. If you know radius, you don't know velocity. If you know velocity, you don't know radius. That violates Heisenberg's uncertainty principle. Is that okay, guys? Moving on to the next one. Yep. Next, nuclear physics. Standard things. Unit of mass in nucleus, we'll use AMU. 1 AMU is 1.66 10 to the power minus 27 kg because the masses are very small. Okay, that's why you use atomic mass unit. And inside the nucleus, you have 2 types of particles. One positive charge, which is protons. Second is neutral, which is neutrons. Now, the atomic mass number is the number of protons plus the number of neutrons. Remember that. This decides your chemical properties of that element. Neutron just creates more isotopes of that particular element. If you want to create isotopes, you change the number of neutrons, you will see it will create isotopes. So the mass number will change, but atomic number will remain the same. Mass of proton and mass of neutron are roughly the same, equal to this, whatever I have put over here. 1.66 10 to the power minus 27 kg. That's approximately the mass of protons or neutrons, whereas the mass of electrons is typically in the order of 10 to the power minus 31 kg. That's very, very small as compared to this. You will see that when you look at the nucleus of an atom, so let's say this is your protons and neutrons like this, example. This is your nucleus, and maybe the electrons are going in orbits like this. These are your electron orbits, example. So obviously you can see the nucleus has some size. So this is nothing but your nucleus. The radius of the nucleus is given by this formula. R is equal to R naught A raised to 1 by 3. A is the atomic mass number. R naught is 1.2 10 to the power minus 15 meters. It's very, very small. Also keep this in mind. Density of all the nuclei are basically the same. It's not different. Take hydrogen or helium or aluminum. It's all going to be the same, irrespective of the number of particles. Particles per unit volume is the same. So it does not matter. So I think I mentioned this also. What is Z? What is N? What is A? Z plus N is atomic mass number. And what is the meaning of isobars, isotopes, and isotones? You should know that. Isotopes is where you have different elements of different atomic mass number. If you have number of neutrons same, it is isotones. If it is same protons, it is isotopes. Keep this in mind. Standard thing. Now, what is the job of neutron? It is to stabilize the nucleus. Keep this in mind. So without a neutron, a nucleus will never be stable. All the protons will just fly out because of electric repulsion. Neutrons are the ones which hold the particles together. Now, whenever a nucleus is formed, you will see there is some kind of a mass defect which is created. If you measure the individual masses and the mass of the nucleus separately, they are going to be different. Expected versus reality, the difference is called as the mass defect. And that mass defect leads to a tremendous release of energy. Einstein said that mass and energy are equivalent to each other, and energy is m into c square. If you destroy m mass, then E energy is created, which is equal to mc square. If you create a mass, then energy will be destroyed of the same amount. So this is energy and mass are interconvertible, and the relationship between them is given. So if I call all the protons and neutrons inside a nucleus, you will see the mass will slightly be lost. That mass lost is mass defect, and that will release energy, which is called as the binding energy. That is also called as the energy required to bind these bind these protons and neutrons together inside the nucleus. This is delta mc square. This is your mass defect. This is your mass defect. And you can also write it as 931 into delta m mega electron volt. It's up to you if you want to use this or this. This will simplify your calculation. But keep this in mind. This delta m should be in atomic mass unit. Then only use this formula. Else you can use this formula. It's up to you. Okay, cool. Let's move on. This graph is very important, guys. Stability of the nucleus. So if you measure the binding energy from this and you divide it by the number of nuclear particles, that means protons and neutrons, what you get is the binding energy per nucleon. Right now, this is simply put binding energy, right? This is simply put binding energy. But if you divide it with the nuclear particles, that is atomic mass number, what you get is basically the binding energy per nucleon. Binding energy per nucleon, per nuclear particle. This one. If you draw it for all the graphs, all the elements, it increases till iron, and after that it decreases for heavy elements. When the energy required is good, that means the energy released when the nucleus is formed is good, then that atom or that nucleus is very stable. So hence it is said that iron is the most stable nucleus, because the energy released when it is formed is the highest per nuclear particle. More energy which is released, that means it will go to a lower energy state and it will become more and more stable. So that's why these elements want to become iron. They are idealizing iron. These elements are idealizing again iron. They want to be this. So when they try to become iron, they will have to combine together to become iron. That means they will have to fuse together. If these people want to go here to increase their binding energy per nucleon, they will have to disintegrate. That means split, that is fission. Fission, and this is fusion. So when they meet, it is fusion. When they separate, disintegrate, it is fission. Keep this in mind. Okay, so very, very important graph. So this always tells you about the stability. Stability of whom? Of the nucleus. Keep this in mind. Stability of the nucleus. Everyone? Okay. So I have mentioned that over here as well. So heavy nucleus tries to disintegrate. Lighter nucleus tries to integrate itself and form heavier nucleus. This is also very important. Now, you will see in your textbook, there is something called as nuclear force. You don't have the formula. It's not there. Only if you do PhD, you will see it. Nuclear force is the force which exists inside the nucleus to hold the protons, neutrons together. Else proton will repel and fly out. So the job of the neutron is to hold them together. So what is the meaning of nuclear force? There are some pointers. Please go through these pointers. It can come like a paragraph. Explain nuclear force. Characteristics of a nuclear force. Nuclear force is stronger than Coulomb force. Nuclear force can dominate over the Coulomb force or electric force. It's because it's the strongest force in nature. Also, the nuclear force is at a very small distance. It does not act at meters or centimeters or even Armstrong. It acts only till few 10 to the power minus 15 meters. You can see that nuclear force falls rapidly to zero if the distance is more than few femtometers. Femto is 10 to the power minus 15. Whereas electric force dominates from Armstrongs. So if the distance is few Armstrongs, electric force is strong. Here in Armstrongs, there is no nuclear force. So also you will see the neutron, proton, all these particles can have basically nuclear forces, but it does not depend on the charge or the mass. It depends on the spin. The force does not depend on the charge or the mass. It depends on the spin of these particles. Okay, so some things which are very, very important. Cool. Can we go ahead to the next chapter, guys? Ready for the last chapter, I guess? In semiconductors. Yes. Expect petroleum, depend on PYQs and NCRT, but expect around 80% questions to 70% questions. There could be some extra things as well. Okay. So, going on over here, metals, non-metals and semiconductors, you should know the approximate conductivity of metals, semiconductors and insulators. And they might ask you, differentiate between conductors, semiconductors and insulators. You know what is the meaning of conductors. I had given it to you in the chapter of current electricity at the start of the class. The passage of the electricity is very easy. They allow the passage, that is conductor. They have very less resistance, very strong conductance. Semiconductors are in between of insulators and metals, or you can say conductors. So they have conductivities in this range or resistivities in this range. Remember, resistivity is 1 upon conductivity. Another important formula right over here. Another important difference between conductors and insulators is that, or semiconductors is that, in metals, when you increase temperature, you will see that the resistance increases. So for metals, if temperature increases, resistance increases. But for semiconductors, when temperature increases, resistance decreases. Another important difference. Here there is no resistance, well, no change only, because it does not allow only anything to pass. So there is no point talking about resistance for bad conductors or insulators. Main thing is difference over here between semiconductors and conductors. Okay, keep this in mind. You can also give examples of metals, non-metals or non-conductors, and also semiconductors. Do not forget to give examples. Okay, if you miss examples, you might lose some marks, maybe half a mark over there. So don't want to lose that. So semiconductors examples, silicon, germanium. But you can also have many more kind of semiconductors which are made of multiple elements like compounds like CDS, GAS, CDSE, or basically indium and phosphorus. So all these things can combine as compounds to also make semiconductors. Now you can have two types of semiconductors. Now it all depends on the band levels and the band energies. Remember, in semiconductors you always have something called as the filled bands, which are called as the valence bands, and then you have the empty or half filled bands, which are called as the conduction bands. So if an electron is in the conduction band, it can easily conduct, and if you don't have electrons, it will not conduct. This gap is called as the band gap. This is called as the band gap. So first of all, you should know what is valence band, you should know what is conduction band, and you should also know the gap between them is basically called as the band gap, which decides whether it is a conductor, insulator, or semiconductor. Now what happens is, if this gap is large, it will be very difficult for these electrons to enter the conduction band. This is your conduction band. If this gap is very small, easily they can jump and they can conduct electricity. So this gap decides the distinction between conductors, insulators, and semiconductors. Keep this in mind. In fact, I have shown it to you over here. You should, if it's a big question like for 4 marks, you should also show the energy diagrams for conductors, semiconductors, and insulator. If it's a 1 or 2 mark question, I don't think it will be needed. But if it specifically asks for energy level diagrams, do not forget to show these diagrams. Like if you notice over here, if the bands are overlapping, if the conduction band overlaps with valence band, then what will it be, guys? It will be a conductor. It will be like a metal. If you see that the band gap is much larger than 3 electron volt, very large, that's it. It's going to be very difficult to shift these electrons here. It is going to act like an insulator. If the gap is there, but not so much, but it is not overlapping also, then it is a semiconductor. So this is basically for a conductor. This is basically for a conductor. This is basically for a semiconductor. And this one is basically for an insulator. So you should know the difference. 3 electron volt is the cutoff. Below 3 electron volt, semiconductor. Above 3 electron volt, bad conductor, insulator. If they overlap, it's a very good conductor. That's it. Okay. I hope this is clear. Everyone with me? Everyone with me on this? Okay. Now the semiconductors that you have, okay, they will have certain free electrons which will be moving. There will be vacancies which are created. They are called as holes. This vacancy of electron is called as holes. There will be also free electrons which are negatively charged, okay, and these together conduct electricity. Negative charges will be going one way, the emptiness, the vacancy, holes will be going the other way. Both of them are responsible for current. So the total current is the current of the electrons plus the current of the holes in case of semiconductors. Remember, in conductor, there is no hole or something like that. There is only flow of electrons. Only the electrons move. That is the difference between conductors and semiconductors again. You will also see that the number of electrons and the number of holes are same, and that is a constant given by Ni. That will be different for different materials. If it's germanium, it's different. If it's silicon, it's different. So it depends on the material, guys. Okay, I hope this is understood. Yep. So numericals are there, bacha, quite significant, something which you cannot ignore. If you just do numericals, you will not get good marks. If you just do theory, not good marks. If you do both only, you will get good marks. So you cannot leave numericals. You cannot just be dependent on numericals. That's how the weightage is. So another important formula over here, any number of holes or electrons, Ne is electrons, NH is holes, and that is the intrinsic semiconductor concentration. It's the number per unit volume. That's the concentration of the electrons or the holes. Okay. Yep. We'll be doing numericals tomorrow. Actually, tomorrow 100 questions. Day after tomorrow PYQs. After that, sure short questions which are going to come. Okay. Is that okay? Cool. Now, okay, I think I mentioned this in the previous slide. All right. Now, fair enough. Now, when you add certain materials like pentavalent or trivalent impurities, you get N or P type of semiconductor. You should know that. So if you add valency of 5 pentavalent like arsenic, antimonium or phosphorus, then you get a N type semiconductor. If you add trivalent impurities like aluminum, indium, boron, then you get P type of semiconductor. You should know the diagram, you should know the energy levels, everything. So when you add extra electrons, it is N type. So electron concentration increases, hole concentration decreases. If you add vacancies, then the hole concentration increases, electron concentration will be less. It will make it P type of semiconductor. In either of the cases, whether it is N type or whether it is P type, one thing is for sure, that Ne into NH is still going to be a constant, and that will be equal to Ni square. Remember Ni? Number of electrons or holes in intrinsic semiconductor. This semiconductor, N type or P type, is extrinsic type. You are adding something externally, you are doping it. So the product of electrons into holes is constant. If electrons increases, holes reduces. If holes increases, electrons reduces. Their product will be constant. That's something which you should know, whether it is this or that. Now there are two kinds of biasing. Yep, there are two kinds of biasing, guys. One is forward biasing, one is reverse biasing. You should know all those kind of biasing. In forward bias, whether diffusion is more or drift is more. So remember, in forward bias, the diffusion current is more than the drift current. The diffusion current is more than the drift current. Whereas in the reverse bias, you will see the drift current is more than the diffusion current. You might be wondering, what is this diffusion? What is this drift? Guys, diffusion is basically when the electrons go from N type to P type. They keep going from N type to P type, that is diffusion. When the electrons go from P to N type, that is drift. So diffusion happens the moment you bring these two together. Electrons jump from here, N to P. Some electrons will jump from here to here. That is drifting. Okay, so these both currents are there simultaneously. When there is nothing connected, then both these currents cancel. But in forward bias, then the diffusion current overpowers. In the reverse bias, the diffusion current becomes less and there is a negligible amount of current which flows in the circuit. So you will see that in the forward bias, the currents will flow properly. There is a good amount of current which will be flowing into it. And in the reverse bias, you will see that negligible current will flow. This is graph of your current versus voltage. You can see in forward bias, it picks up. In the reverse bias, hardly any current is there. If you're wondering why it picks up after some time, that's because of a phenomena called as the depletion region and a barrier voltage. When these electrons jump from here to here, they create a wall of electrons and holes which acts like a barrier for more electrons to go from here to here or there to here. That barrier is basically called as the barrier voltage. Okay, I hope this is understood, guys. Okay, great. Moving on. Now, all these things are basically theoretical type. Just go through it, guys. I have put up all the important pointers for all of you. Then also go through, I'll tell you what else you should go through. You should go through diode as a rectifier, the diagram, the waveform, and what is the meaning of rectification, converting AC into DC. You should also know specific examples or applications of diodes like Zener diode as a voltage regulator, photodiode or LED. All these diagrams, their uses are very important. Okay, so just go through it once. I've just kept few slides just to tell you, because today's lecture is not about theory, it's mainly about formulas. Okay, so just go through that. All right. Now, why is photodiode in reverse bias? There is a beautiful paragraph. Understand that's because of this graph. See, over here, when you see in forward bias, the currents are very large. In reverse bias, the currents are very small. Now, what happens in a photodiode? When light falls, the conductivity changes. So the current changes. Now, imagine you're using the photodiode in forward bias. Let's say some amount of light is falling onto it and the current is, let's say, 20 amperes, example. Now, some more light falls onto it. More light falls onto it. Now, the current changes to 20.1 ampere. There is some change in the current because the light's intensity has been increased. Now, imagine another situation where it is in reverse bias. Some light is falling onto it. Very small current will flow, maybe just 10 milliamperes or 10 maybe microamperes, very, very small current, guys, 10 microamperes. Now you increase the light, more light. Now the current increases. Here it changed by 1.1 ampere, right? Imagine such a change happens here. Like maybe it becomes 200 microampere, example. Do you see the changes are significant here? This is very small value. If you change the intensity, the changes are small, but for that small current, the changes look big. Here, even if it is a good amount of change, 0.1 ampere, for 20 amperes it looks small. So don't you see the sensitivity has been increased? That's the reason why you use a photodiode in the reverse bias. Is that understood, guys? That's what is mentioned in the paragraph. So diodes as gates, I don't think it's there. But if questions come on gates, logic gates, I think it is a deleted part. You can just go through it. So there are three kinds of gates mainly that you should know. NOT gate, which inverts the output. Yes becomes no, false becomes true. That's a symbol for it, NOT gate. Okay, it's going to flip the output. Then you have your AND gate or OR gate. So this is OR gate in this case. So only when both are true, the output is true. And then you also have the AND gate, only when, my bad. In OR gate, what will happen? Either one of them is true, then the final output will be true. If both are false, only then the output is false. That's OR. Either this or this is true, then the output is true. In AND, only when both are true, the output is true, or else, even if one of them is true, other is false, the output is false. These are the main things you should know. And also NAND gate and NOR gate, which is basically AND gate and a NOT gate. So you are negating the output of AND. So whatever 0, 0, 1 you are getting, now you will get 1, 1, 1, 0. Same way, NOR gate is a OR gate with a NOT gate. So if you are expecting 0, you will get 1. If you are expecting 1, you will get 0. It's negating the output. So all these things, truth tables, the diagram, again important, but I think it's from the deleted part. Okay, so that's it from my side. So I think I have touched upon all the major formulas. So I think that should be more than enough for all of you. Probably a few things in communication systems and all that, if you want to, just go through the textbook. Main thing is the range formula that you should know in communication systems. The second thing is the modulation index formula, carrier signal waves ratio. If you know that is the modulation index, that's more than enough. There are only two formulas. One more formula you can think of is the minimum size of the antenna required is lambda by 4. That is given in the textbook. Just go through it. And the power is basically inversely proportional to the wavelength. That's also mentioned in the textbook. So these are some important points in communication system. Other than that, it is just theory. Sky wave, space wave, ground wave, what is modulation, what is FM modulation, explain which wave will, or how will you communicate between here and here, or derive the formula for the range between two transmitters and receivers. So these kind of things can come in communication systems, right? So, but that is again dependent whether you are preparing for JEE, NEET, and which year you are going to see this video. All that, sometimes it will be deleted, sometimes it will come. So maybe you are going to watch this video after 1-2 years, and maybe that time the communication systems chapter is there. Some 2 years later, maybe it is not there. So just mention that bit over here. Okay, is that okay, guys? Everyone? So you're going to get the PDF where? On the Telegram channel. Where is the Telegram channel? Link in the description box. Perfect. So this was a very long video. Now I'm also very hungry. I'm pretty sure you too are hungry. Go ahead, jump on your snacks, take a break, and sit for studies at 5 o'clock. What are you going to do today? You would have understood what are your strengths and what are your weaknesses. I want everybody to post your weaknesses or topics which are difficult. And after the video is over, you're going to put it up in the comments. Today, I'm going to do electromagnetic induction and semiconductors and electrostatics. Whatever is difficult for you, just do that. It's up to you. It could be anything. And if you feel that, sir, I need more lectures, I want to watch more lectures of yours, is there a way? Yes, you can just go to playlist. And solution for every problem is just use the search bar and just search Shreyas Sir, let's say electrostatics. Shreyas Sir, electrostatics. If you just search for it, that's it. Your solution is here. One beautiful playlist will come. Just open it up. Okay? So that's how easy it is to search for my videos, guys, in YouTube. So you can make use of that. Today is going to be doing difficult topics. Tomorrow, you will try to complete the next difficult topics. What else you have to do, I'll tell you. Okay? But today, you will do only difficult topics through the videos or through your notes or through NCERT, whatever you want to do. Just do difficult topics or things which you are not liking, things which you hate, or things which are your weak points where you do not have confidence. Just do that today. Till what time are you going to study? 11 o'clock. So I would suggest finish off your lunch, everything, whatever is there, or finish your break by 4 o'clock. Sit for studies. Take breaks after every 1-2 hours and take your dinner at maybe around 9 o'clock. Till 11 o'clock, you will study. Again in the morning, if you want, read more. And tomorrow at 10:30, I will meet you for solving problems of MCQs basically, or assertion reason, and also your case studies. That's at 10:30 tomorrow. That lecture will not be very big. It will be a small lecture only because it's just problem solving. But make sure you attend it tomorrow and get in your friends as well. And if you are loving these sessions, do not forget to hit the subscribe button and also smash the like button. It means a lot for me, because for all the efforts that I put in for all of you, I think I should deserve a small like at least. Okay. Thank you so much, guys, for being here. PYK session is there day after tomorrow. Yeah, numericals will be done tomorrow as well as day after tomorrow and even the day after that. Bye bye, guys. Put up your comments on what are your difficult topics and what are you going to do today, so that when you come tomorrow, I'm going to see, okay, these people have done this, or these people had kept a target of this. I'm going to ask you guys. Okay. See you. Bye bye. Have a great time. Hasta la vista, Captain Shreyas signing off.